So in the previous lecture, we have started this problem, design of post-tension pre-stressed concrete slab bridge, and we have covered the calculation of depth of span, then calculation of effective span, then calculation of bending moment due to dead load, bending moment due to live load, and shear force due to dead load and live load. We have also checked the minimum section modulus, which is found to be okay, and the section selected is adequate to resist the service load without exceeding the permissible stresses. In this lecture, we will start from here by finding out the minimum pre-stressing force. So this is the expression to find out the minimum pre-stressing force. So since our section is rectangular, the section modulus at the bottom will be equal to section modulus at the top. So is equal to FB plus FT divided by 2. So how to calculate FT? This is the expression to find out the FT value, FTT minus MD divided by ZT. So as you know, the permissible tensile stress is equal to 0. MD value we have already calculated, 186.04 into 10 to the power 4 divided by ZT, section modulus at the top, that is equal to the section modulus at the bottom. This is calculated as 41.67 into 10 to the power 6. The FT value we got minus 4.46 Newton per mm square. Similarly, this is the expression to calculate FB, that is the stress at the bottom, that is equal to FTW divided by eta plus MD plus ML divided by eta ZB. So this first term becomes 0 as the permissible tensile stress is equal to 0 plus MD is 186.87 plus ML 186.04 into 10 to the power 6 divided by the loss factor is 0.8 and JB 41.67 into 10 to the power 6. So we got a value of 11.19 Newton per mm square. Now putting all these values in the expression of a minimum pre-stressing force, that is P minimum, we got a value of 16,162.5 kilonewton. And it is given that we have to use Fractionate cable containing 12 wires of 7 mm diameter stressed at 1200 Newton per mm square. So the total force we can calculate here. The area of each wire is pi by 4 into d square, multiply with 12 number of wires, and in each wire is stressed to 1200 Newton per mm square. So the total stress is equal to 554 kilonewton. So from here we can find out the spacing of cable for 1 meter. So 1000 divided by minimum pre-stressing force is 1682.5 divided by 554, which is equal to 329 mm. Now the next step is to calculate the eccentricity of cable. So this is the expression to find out the eccentricity at the center of the span. ZT ZB FT minus FB divided by A into FT ZT plus FB ZB. So by putting here ZT is equal to ZB, which is equal to Z, the expression becomes this, and all the values we have already calculated. Just put all the values here, so you get a eccentricity of 190 mm. Now the cables are arranged in a parabolic profile with maximum eccentricity of 190 mm in the center of the span, and it reduced to 0 at the support. So next step is check for stresses at service load. So these values already given. The prestressing force 1682.5 kilonewton, eccentricity we have used 190 mm, then area section modulus 41.67 into 10 to the power 6 calculated, then dead load moment 186.04 kilonewton meter calculated, then live load moment 186.87 kilonewton meter, this is also calculated. Then the expression for stress, so we can find out each term one by one. This is the direct stress, that is P by A. uh, mm, so this is coming 3.365 Newton per mm square. This is the stress due to eccentricity, that is equal to 7.672 Newton per mm square. Stress due to dead load, that is equal to md divided by section modulus Z. So 186.04 Newton to the power 6 divided by 41.67 into 10 to the power 6. This is equal to 4.465 Newton per mm square. Then the stress due to live load moment, we got 186.87 into 10 to the power 6 divided by 41.67 into 10 to the power 6. So you got 4.484 Newton per mm square. Now you can calculate the stress at transfer and stress at service period. So while calculating the stress at transfer, we have to consider this direct stress, then the stress due to eccentricity, then stress due to dead load. Because during transfer of pre-stress there will be no live load. So at the top it will be P by A minus P by Z plus MD by Z. P by A minus P by Z plus MD by Z, which is coming 0.158 Newton per mm square. Similarly at the bottom the expression will be P by A plus P by Z minus MD by Z. So after putting all the values, we got 6.572 Newton per mm square. Now the stresses at service period, it will be so during the service period there will be loss in the pre-stress. So after deducting the stress due to losses, the expression becomes eta times P by A minus P by Z plus MD by Z plus ML by Z. So this is the expression for stress at the top during service period. So after putting the values, we got 5.503 Newton per mm square. Similarly at the bottom it will be eta into P by A plus P by Z minus MD by Z minus ML by Z. So after putting the values, we got a value of minus 0.119 Newton per mm square. And the actual stresses developed are within the permissible limit. The next step is check for ultimate flexural strength. The expression to find out the maximum, the expression to find out the moment of resistance of the rectangular section is mu is equal to FPB APS into D minus 0.42 x2, where FPB is the tensile stress in tendon at failure and APS is the area of pre-stressing. So in this expression we have two unknown, that is FPB tensile stress in tendon at failure and XU, that is the depth of neutral axis. And this APS that we can calculate the area of pre-stressing. So 12 number of wears of diameter 7. So 12 into pi by 4 into 7 square into 1000 divided by the spacing 329, that is equal to 1404 mm square. Then D, the effective depth is 445 mm. So now these two unknown values FPB and XU. It can be obtained from table number 11 of IS 1343/2012. So we'll check that. Table number 11. Okay, so you can see here table number 11. The conditions at the ultimate limit state for rectangular beams with pre-tension tendon or with post-tension tendon having effective bond. So the value of APS FPU divided by BD FCK for different value, you can have here the this first two column. This is for to get the value FPB divided by 0.87 into PU, and this two column, this is for XU by D value. The first column for pre-tensioning and second one for post-tensioning with effective bonding. So here also this first column is for pre-tensioning and second with post-tensioning with effective bond. That is your bonded post-tensioning. So first you have to calculate this value, then accordingly you can get the values of this and this from this table. So APS FPU divided by BD into FCK. So APS we have calculated 1404, then FPU is given 1500 divided by, since we are designing for 1 meter of width, so B is taken as 1 meter, that is equal to 1000 mm into depth of the section is 445 mm into FCK used is 40 Newton per mm square. So after calculating this, we are getting a value of 0.118. So from table number 11, for a value of 0.1, this value FPB by 0.87 FPU is 1 and XU by D value is 0.217. Similarly for 0.15, this value is 1 and this value is 0.316. So we can do linear interpolation because we want to find the corresponding value of FPB and XUD for 0.118. So it will be here 0.118. So this value will be 1 and XU by D value we can got from linear interpolation, which is 0.256. Now the value of FPB will be 1 into 0.87 into 1500, that is equal to 1305 Newton per mm square, and XU value 0.256 into 445, the depth, effective depth. So we are getting a value of 113.92 mm. So after putting the values in the expression of moment of resistance mu, we are getting 727.67 kilonewton meter. So now we will check whether this is within the limit or not. So what is the mu required? Mu required will be 1.35 times dead load moment plus 1.5 times live load moment. So if you calculate this, we are getting a value of 531.46 kilonewton meter, which is less than 727.67 kilonewton. So our moment of resistance of the section is more than the required moment from the external loading. So thus the section is safe here. Okay. The next step, check for ultimate shear strength. So the expression for ultimate shear force, that is Vu is equal to 1.35 the dead load shear force due to dead load plus 1.5 times the shear force due to live load. So we have already calculated the shear force due to dead load, that is 71.35, and the shear force due to live load is 81.75. So putting the values here, we got a value of ultimate shear force of 217.72 kilonewton. Now we'll compare whether this shear force, the value of shear force is more than the design shear resistance or not. So from the code we can get the expression to find out the design shear resistance at the support section, which is equal to VRDC is equal to IBW divided by S root over of FCTD square plus minus K1 sigma Cp FCTD plus eta P sin theta. So in this expression, I is the second moment of inertia, that is equal to BDQ by 12. So which is coming to be 10.42 into 10 to the power 9. Then S is the first moment of area between centroidal axis and compression fiber above the centroidal axis, which is equal to B into the area will be B into D by 2. This will be this is B, this will be D by 2. So this is the centroidal area between centroidal axis and the compression fiber above the centroidal axis. Okay, so will be D by B into D by 2, and this will be D by 4. So after calculating, we got 31.25 into 10 to the power 6 mm cube. Then FCTD is FCT divided by gamma m, which is equal to design value of concrete tensile strength. As you know, FCT is equal to 3 for FCK of 40. So it will be 3 by 1.5, that is equal to 2. Then sigma Cp is the mean compressive stress at centroidal axis, that is eta P divided by AC. So just put all the values here, then we'll get a value of 2.7 Newton per mm square. K1 is a constant, that is taken as 1 for post tensioning. Then theta is the slope of cable at the support, that is equal to 4E by L. Which is coming 0.073. So after putting the all the values in the expression of VRDC, it is coming to be 1121.552 kilonewton. So this is the design shear strength of the section, which is more than the calculated shear force, that is 217.72. So this is okay. The shear resistance of the support section is more than the required ultimate shear force. So the structure is safe in shear. Now the next step is calculation of supplementary reinforcement. So as per clause 16.5.1 of IRC 112, the minimum longitudinal reinforcement should be equal to 0.26 times FCTM by FYK into the area, that is BTT, and it should not be less than 0.0013 BTT, where BT is the mean width of tension zone. And we can calculate this value, and the minimum value of longitudinal reinforcement, that is 0.26 into FCTM we have calculated already, that is equal to 3 divided by Fy is 415 into 1 meter width into 445 effective depth. So this is coming to be 578 mm square, and it should be more than 0.0013 times the area, that is BT into D. So it is coming to be 836 mm square. So we have to use this value as AST minimum, because it should not be less than this value. So if we assume 10 mm diameter bars of Fe415 HYSD bar, both at top and bottom of the slab, so we can find out the spacing for 1 meter of width, that is equal to 1000 divided by total area AST is equal to 836 divided by area of each bar, that is 5 by 4 into D square. that is equal to 187.89 mm. So we can take little bit less than the required spacing, that is equal to 180 mm. So let's provide 10 mm dia bars at a rate of 180 mm center to center spacing both at the top and bottom face of the slab in longitudinal and transverse direction as supplementary reinforcement. Now the next step is check for deflection. So we have to find out the deflection, the maximum deflection due to pre-stressing force, then the deflection due to the dead load, the deflection due to the live load. The total deflection will be combination of these three. So the expression for maximum deflection due to pre-stress AP, since this is a parabolic cable, so the expression is 5 by 48 P dash EL square divided by AC into I, where P dash is equal to eta times P after the losses. So 0.8 times 1682.5, that is equal to 1346 kilonewton, and EC is given 33 kilonewton per mm square modulus of elasticity. So after putting the values here, 5 by 48 into 1346 into eccentricity, we have taken 190 into length is 10.4 meter divided by EC 33. I already calculated 10.42 into 10 to the power 9. So you are getting a value of 8.38 mm, and it will be upward. The deflection due to pre-stressing force will be upward or positive. Then next, to find deflection due to dead load AD. So since this is the dead load is a uniformly distributed load, so to calculate this, the expression is 5 by 384 WD L to the power 4 divided by AC into I. So just put all the values here. Dead load we have already calculated, that is 13.76 kilonewton per meter, or if you take all the values, the unit of all the values in kilonewton in mm, so it will be 0.01376 kilonewton per mm, and length is 10.4 meter, then AC 33, EII 10.42 into 10 to the power 9. So the deflection due to dead load is 6.2 mm, which is downward. Then AL is the deflection due to live load, that will be WLQ or QLQ divided by 48 EI, where Q is the total live load, which is already calculated 19.58 kilonewton per meter square. So 19.58 into length of the load is 4.76, that is equal to 93.2 kilonewton. So just put the expression here. So after putting all the values, we got 6.35 mm downward. Here downward deflection will be taken as positive, and deflection due to pre-stressing force, that is upward, will be taken as negative. So add all the deflections to get the total deflection. So the total deflection is coming 4.17 mm, and the maximum permissible deflection due to live load only, as per the code, it is span divided by 800, so which is coming to be 13 mm, and 13 mm is the permissible deflection due to live load only. So you can check here the deflection due to the live load in the design problem is 6.35 mm, and the permissible deflection due to live load is 13 mm, so it is okay. Next is design of en block reinforcement. So at support section, Concentric cables carrying a force of 554 kN are spaced at interval of 329 mm, and the end block has to be designed for bursting tension due to the encouraged force. The bursting tensile force is obtained using IRC 112 2011 table number 13.1. So in this code IRC 112 row 2011 table number 13.1, that is a table. This is the table. So the first line, this is YPO divided by YP naught divided by Y naught, and the second one FBST divided by PK. So YP naught is the dimension of the plate at the end block, and Y naught is the dimension of the this one. So for different values of YP naught by Y naught, different values of FBST divided by PK is given, where FBST is the bursting force and PK is the pre-stressing force. So in our case, the PK value is 554 kilonewton, and this YP naught value is 150, and Y naught is 329 mm. The spacing we have taken 329 mm. So this ratio will be 0.456. So the corresponding value of FBST by PK is 0.207 from table number 13.1. So FBST value is equal to 0.207 into PK, that is 554, that is equal to 114.68 kilonewton. And if we use 10 mm diameter bars of Fe415 as N block reinforcement, the area of steel to be required to resist this bursting force is equal to FBST divided by sigma S, that is equal to FBST divided by 0.87 Fy. So it is 114.68 into 10 to the power 3 divided by 0.87 into 415, that is 318 mm square. And the spacing to accommodate these reinforcing bars of area 318 mm square can be calculated for 1 meter width, that is equal to 1000 divided by 318 divided by pi by 4 into d square, that is 246.98 mm. So let's provide 10 mm diameter bar at a rate of 100 mm center to center spacing in vertical and horizontal direction as a mesh in front of the anchorages at 100 and 200 mm respectively. Now this is the cross section of deck slab at center of the span. This is the figure showing cross section of the deck slab at center of span. So this is the tendon, 12 number of 7 mm dia cables. They are the tendons. Then the supplementary reinforcement, I have taken 10 mm dia reinforcement, 180 mm center to center spacing both at the top and bottom and in both the direction, both transverse and horizontal direction. The total depth is 500 mm. This is the wearing cord thickness. Then this is the hanging bar. There are 4 number of hanging bars of diameter 12 mm. Then so this is all about your design of pre-stress concrete slab bridge